Our goal is to implement the EveCore microcontroller in Verilog. A good place to start is with a high-level view of the entire project. So here is the overall structure of the FPGA we're designing. In this diagram, each rectangle represents a module, and so we see our core as well as a couple of UART related modules and a module called output control. The UART transmit and UART receive modules are concerned with interfacing to a UART serial communication channel, and they will serialize the data that's coming in on the receive channel and going out on the transmit channel. These, of course, are rather complex and they contain state. We'll discuss these elsewhere. The output control module is used for debugging our core. It is purely combinational, and it takes input from the core and displays it on the 7-segment LED display. So it will have two instances of our module called 7-segment decoder, and that module just translates a 4-bit nibble into the 7 signals that we need to send to the 7-segment display. And it will also take as input the values of the buttons, so we can press buttons on our board in order to display various values that we're interested in. So the core will send a number of different values to the output control module, and then while it's running we can press buttons to see those values, and this will allow us to look at a number of different things. Even though we only have 2 digits of the 7-segment display, that's only enough to display a single byte, and we want to display several different things, of course. Now within the core module we have the ROM memory, the RAM memory, the registers module, we have a module for instruction decoding, and we have the ALU module. The ROM will be completely combinational. In other words, we'll feed an address in and we'll get the corresponding byte from the read-only memory out. It will be combinational, at least initially. We may talk about some other approaches later. The RAM module, of course, will have state, and so we supply an address, and then on the next clock we can get data out of the RAM, or we can set values and store values into the RAM. The module called registers will contain and encapsulate the 8-bit registers. The module for instruction decoding is purely combinational. It will take as input the 8-bit opcode from the current instruction, and it will decode this and figure out what instruction we've got and pull out several fields of interest. So this will take as input the 8 bits that are coming from the instruction register, which I haven't yet introduced. And finally we have the ALU module. This is also combinational. It takes basically 2 8-bit inputs, and these will come from the A and B registers, and it produces an 8-bit output. It also takes as input a function code and the previous value of the carry, and it produces also the future value of the various condition code registers. Okay, so let's take a look at the core module a little bit more closely. To interface with the outside world, we have I/O registers. So in the EveCore, to output something, we can use the out instruction to update an output register, and we can read from devices by using an in instruction. So when we execute an out instruction, we have these 4 channels that will be active, and will basically send data from the core, more precisely from the accumulator register, to one of the I/O registers. And when we execute an in instruction, we will be asking for data from one of the peripheral devices, and we'll of course be storing that into the A register, and these 4 channels right here will be active in the in instruction. And I mentioned the output control module that we'll use for displaying debugging output. This is strictly a one-way communication. The core will be sending values of interesting things, such as the program counter and the state and the instruction register and so on, to the output control module. So from the point of view of trying to understand the control, we really can kind of ignore the debugging output. Now, of course, our core will have state and it will be clocked, so we have a clock input. We'll also be able to single step the core, so we have the value of the single step button, and that will tell us when the button is pressed. So when we're running in single step mode, we will be able to push a button and execute a single clock cycle and see what the debugging output is and sort of see how the thing runs. We also have a reset input, so we can reset everything and start over again. So now let's look at the additional state. Of course, the RAM, the registers contain state, but in addition to the values in the registers, we also need a program counter, a stack pointer, and we will also have an instruction register and a register which I call MSB for most significant byte. So the program counter is the 16-bit register that tells which instruction we want to execute next. So it will always be pointing at some location in the ROM, and that's where we will be fetching the next instruction from. The stack pointer is also 16 bits, and we'll use that, of course, when we execute the push and pop instructions. The way this core is going to work is it's going to, in one cycle, read a value from the ROM and store it in the instruction register, and then in the next cycle it will be executing that instruction. And we'll see a little bit of pipelining, so many instructions will take only a single cycle on average. So the 8-bit instruction register will hold the opcode of the instruction that's currently being executed. And for some instructions, we have a 16-bit immediate value. For example, when we want to load from memory, we need to get the 16-bit address, so we'll increment the program counter and we'll get a byte. That would be the most significant byte. And for the moment, we'll store it in this 8-bit register called MSB. And then we'll increment the program counter and get the least significant byte from the ROM memory. And then once we have the most significant byte and the least significant byte, we can actually do the memory operation. We've got the entire 16-bit address, so at that point we can go ahead and do the load or store instruction. But we need an MSB register to hold one of the 2 bytes while we are fetching the next byte. So that's what MSB is, and we'll use it for some other things as well, but I just kept the name MSB. So that's the overall structure of our FPGA, and now we can start to look at the individual modules in more detail.